Today I'm going to be talking about a very powerful tool known as a control chart. But what exactly are control charts and why are they so useful? My goal is to answer those two questions in this video. Before I get into things, I want to pose a question. Here we have two charts where I plotted output data from two different processes over time. Both data sets have the same scale of 0 to 100. My question to you is, are these processes in control? Or is one in control and the other out of control? Let me know what you think and why in the comments below, and by the end of the video I'll tell you the answer and why. First piece of understanding control charts is understanding variation. There are two types of variation, common cause variation and special cause variation. To help us understand these concepts, let's use an example. Think about the time that you get to work every day. Is it exactly the same time? Or would you say you usually arrive between a certain range of times? Say you usually arrive at work between 7:45 and 7:55. with an average time of 7:50. This range represents common cause variation. It is predictable. In other words, your boss can count on you to arrive in this time range, as long as the general process stays the same, that is. But what if your car breaks down? You definitely aren't going to make it to work within the usual time range. This type of scenario represents special cause variation, where there is some atypical cause that leads you to arrive at work way later than usual. Luckily, your boss uses control charts, so as soon as 7:56 hits, he knows something is up and he calls. After you tell him what's happened, he sends a cab and a tow truck and you make it to work even though you arrive much later than usual. Alright, I'm only joking about that. Hopefully your boss isn't using a control chart to monitor when you arrive at work. If that were the case, I'd say he has some serious micromanaging issues, but you get the point. So control charts help us separate and visualize common cause variation and special cause variation. And that's really what separates control charts from your basic run charts or time series plots. But how exactly do we determine what is common cause from special cause? In other words, where do we draw the line on what amount of variation is considered common? Because as we talked about, there's always going to be some amount of variation, but the key is determining how much variation is abnormal. So this is where things get into the statistics, but don't worry, I'll keep things somewhat light for now. Basically, some people that are much smarter than me have come up with ways of determining where we should draw the lines between common and special cause variation in a process. Those lines are called the control limits. The upper and lower control limits are determined first by calculating an estimated short-term standard deviation, or sigma value, based on the dataset used. The standard deviation is just a measure of how spread the data is. Then we add 3 standard deviations above the mean and subtract 3 standard deviations below the mean to set our control limits. For a process that is generally under control, we can then say with some degree of confidence that if a data point falls outside these control limits, then there must be some special cause driving that excess variation. It is very important to note here that we are not simply taking the standard deviation of all the data points to get our sigma value. That would not be correct. The sigma values we want to use are derived using different statistical constants and equations specific to the type of control chart being used. The simple, or maybe not so simple, explanation for this is that these equations and constants allow us to calculate the within subgroup variation, or short-term variation of the process. Using the short-term variation allows us to get a better measure of the amount of common cause variation in the process. To understand this idea, let's say I were to go to a machine and ask an operator to make me 10 samples of a part in a row without changing any settings. Because the samples were taken back to back over a small window of time and we told the operator not to change any settings, any variation between those 10 samples would be from common cause variation that is normal to the process. But now say I waited for the next day and a different operator was running the machine and I asked him to make me 10 samples without changing his settings either. There's a very good chance that there is some variation between this operator samples and the first operator samples because it's a new day, a different operator, the materials may be different, etc. There are tons of tiny variations that could add up to a significant variation between those two sample sets. So because of this, if I were to take the standard deviation of all 20 of those samples, the standard deviation would be larger because that calculation would be including the variation within each sample set and the variation between each sample set. So again, just to drive this point home, with control charting, we are interested in the short-term variation of a process, not the overall variation of the process. For this reason, the standard deviation and control limits are estimated from a measure of the short-term variation and not that overall variation. Another concept that comes up when dealing with statistics and control charting is the idea of signal and noise, so I want to address that now. Signal and noise are really just terms for how we categorize the data on the chart, where signals are points that are outside the control limits and noise are points that are inside the control limits. So basically, special cause variation is what leads to a signal and common cause variation is what just creates noise. And you may also see these terms used interchangeably. So knowing what we know now about control charting, let's go back to the question that I posed at the beginning of this video. are these processes in control? And the answer is yes, both of them are in control. And I know that because I actually put these to the test with my control charting template that I built in Excel, which I'll link to that video in the description. And when I did that, all the data points are in control. In other words, the variation is all common cause or just noise. But we can actually almost see this just visually. The data in both plots are up and down and all over the place, but the amount of variation is consistent around a mean and therefore predictable in both cases. So in control versus out of control is not determined by how much variation from the mean there is in a process, but instead it is determined by whether the amount of variation from the mean is normal or not. And this is a good segue into my last point about control charts, which is that control charts by themselves tell us nothing about the performance of a process. It is common to mistake control limits for specification limits. Specification limits tell us what is acceptable, whereas control limits determine process control. You can easily have a process that is out of control and still meeting specifications, and conversely, you can have a process that is in control and not meeting specifications. So I said that was my last point, but I have one more thing that I briefly want to talk about. There are other rules that can be used to determine special cause variation or signal in a process other than just looking to see if a data point falls outside of the control limits. I won't go into detail in this video, but there are a total of 7 other control charting rules that can help us understand process control. The other 7 rules help us detect patterns that can emerge in the data that represent certain special cause phenomena. So now let's talk about the usefulness of control charts. The first thing that control charts can help us do is to just understand if we are dealing with a process that is in control or out of control. Just understanding this is very important because a process that is in control is much easier to improve or change than one that is out of control. If we monitor a process or gather historical data, analyze it with a control chart, and we find that it is out of control, our first step should be to start diving in and understanding why. Once we understand why, we should work to get the process to a state of control before working to improve it. Until we do this, improvement efforts will be very difficult and it will be very hard to measure or detect any improvements that have been made. Also, if we don't have a process that is generally in control, we won't be able to use the control chart to detect signal from noise in the future. So if we do have a process that is generally in control, we will be able to determine signal from noise. And that is very important because we do not want to react to noise. Again, this is because noise is caused by all of those variations that are natural to the process. If we tried to reduce this variation, it would be at best a waste of resources, and at worst we could actually add more variation into the process. On the other hand, we do want to react to the signals because if there is a signal, that means that there is an assignable cause behind it that is more than just normal variation. Signals tell us when to take action. Signals either tell us something good happened or something bad happened. In the cases where we don't want the process to move, if we see a signal, that means something bad happened. In these cases, we should investigate the root cause and try to correct them. But what if we do want the process to shift in one direction? If we were measuring something like defects, we would want to see defects go down. So if we have a process that is in control and we get a signal that is below the lower control limit, that means something good happened. Either we made a change on purpose and now we have an indication that the change is working, or there was a change that we didn't know about and we should investigate it so we can do more of it.